Okay, I'm going to skip a couple sections here because we can do this without those sections. And I want to get through this because this is the first part of the worksheet that we're going to do on Thursday. And so this has some math involved, and there's another part that has some math involved. Also kind of breaks the math up into two different lectures so we don't have all of it at one time. So here we're going to talk about scientific measurements. Scientists report a measurement very carefully in a very particular way. We do that so that every digit is certain except the last digit. The last digit is always estimated. So here this happened yesterday a lot. So here are two different tables showing the same data. But here the carbon monoxide concentration is reported to the nearest tenth of a part per million. And over here it's just noted to the nearest 1 part per million. So in a scientific measurement, we always assume that the last digit, there's some uncertainty in that. And unless it says otherwise, we would assume plus or minus 1. So this 7.4, we understand that to mean 7.4 plus or minus 0.1. So that would give us a range of 7.3 to 7.5. Right? Over here, where it just says 7, that would be set from 7 plus or minus 1 in the last place, which is the ones place. So this is representing 6 to 8. So this was not measured as carefully or as precisely as this number. And so we report the measurements so that the reader knows how precisely we recorded the measurements. So how do we do that? Well, how many digits you record is going to depend on what device you use. Now, if you use a digital device, which like a digital watch just displays numbers for you, it's easy. You just write them all down. So we have digital balances. When we get a mass from there, we're going to write down all the digits. Okay, easy, just write them all down. Well, the other side of digital is analog. So like that clock on the wall is an analog clock instead of digital. This is an analog balance or scale. So we've got a pistachio on here. It presses the platform down because it has some mass, and then this line moves on the scale. So we're going to ignore ounces because that's an English measurement, and English measurements are stupid. And we're in science class, so we're going to look at grams. So we're looking at this. There's a bunch of lines here, right? And the first one's labeled 0, and this one's labeled 10. So what do each of these lines represent then? 1. They're not numbered because it would just be really messy. But we understand that that's 1, 2, 3, 4, 5, etc. grams. So each line represents 1 gram. We're going to read or estimate between the lines. We're going to read between the lines. So here we see that that line is between 1 and 2 grams, right? Nobody can argue about that. It is at least 1 gram, and it's less than 2 grams. And so when we report 1.2 grams, there is no uncertainty in the 1. Everybody's going to agree it's 1 something, 1 point something. The uncertainty is in the 0.2, because this is just you eyeballing between those two lines. And we might disagree on that. Someone might say, well, I think that's 1.3. Or somebody might say, I think it's 1.2 or 1.1. Well, yeah, there's uncertainty. We can agree to disagree about that. But this recorded digit here, this uncertain digit, is the next decimal place over from what those markings represent. So if we have a ruler where the smallest division represents 0.1 centimeter, the lines are in the tenths place, we're going to estimate the next decimal place, the hundredths. A thermometer with 1 degree markings, we're going to estimate the next decimal place. Okay? We'll be practicing this in lab. But we can also do a little bit of practice right here. So this is a thermometer on its side. It's in degrees Celsius. And so we're supposed to record the measurements. So, we're looking at where the red line is, and we see this it's over here. Well, before we start writing, we need to orient ourselves and say, well, what does each of these smallest lines represent? 1, right? Because, here's 90, 91, 92. So each of these is 1 degree, right? So the marking equals 1 degree Celsius. So then what are we going to estimate to? The tenths. So we look at this and we say, well, that one is real close to the 8, right? No, that's not the 8. It's the 3. I was thinking this was 100 and that was 105. So 100, 1, 2, 3. So it's 103 0.1.
I'd say
102.9. Ooh, no, that's a little different. What would we write if we think it's exactly on the line?
We wouldn't avoid that.
Well, we can actually write that though. So 103, and if we're estimating where that is, and we think it's right on the line, we're going to say 0.0 degrees Celsius. Now, we will learn that there are places where you want to avoid those trailing zeros. But we have ways to get around that as well. Here is a graduated cylinder with some liquid in it. The liquid has a curved surface at the top that's called a meniscus. The graduated cylinder is calibrated to be read to the bottom of the meniscus, the bottom of that curve. We'll learn in a later chapter why it makes that curve. So looking here, we see this is 4 milliliters and that's 5 milliliters. What does each of these smallest lines represent? 0.1, right? So the markings are 0.1 milliliters. So then what do we estimate to? 0.01, the next decimal place. Right? So we're going to look here, and so we've got 4. So this is 4.5, and that's 4.6. So it's more than 4.5. Yeah, so it looks like 4.57 milliliters to him. Someone else might say, well, I think it's 4.58 milliliters. Right? That last digit is estimated. We're not certain about it, but it gives us information, and we want to keep all the information we can. Because this, even though we don't know exactly what it is, it tells us this is closer to 4.5 than it is to 4.4. I'm sorry, closer to 4.6 than to 4.5. Any questions? So we'll be practicing this in lab. Okay, so that's how we record the measurements. Then if we do calculations with those measurements, we can end up with either way more digits or way fewer digits. And what we want to do is we want to preserve the precision of those measurements when we do calculations. Bless you. If we take 1.0 meters and divide by 3, and our calculator says 0.33333333333, forever, well, that would imply that we know that a lot more precisely than we do, when actually the original measurement, 1.0 meters, was estimated to the nearest tenth of a meter. So we have to have a way of keeping track of that when we do calculations. The method we're going to use is known as significant figures or significant digits. A lot of students don't like this, but the alternative is differential calculus. Anybody want to do that? I don't. Yeah, I thought it was cool in college when I learned it, but then, it's just so much work, right? And so I don't even remember how to do that anymore. I just remember it's a thing, right? Significant figures are, once you get used to them, are fast and easy and help us to record our results with the appropriate amount of precision. So the greater the number of significant figures, the greater the precision of the measurement. So the first thing we have to do is learn how to count the significant figures in a number. So these are the rules, and just like with, when you're playing a new game, you read all the rules and you're like, oh, this isn't going to be fun. I can't remember all of this. But then you start playing the game and it starts to make sense to you, and then you don't need the rules anymore, right? You just remember how it works. So right now we're in the reading the directions stage of playing the significant figures game. And it's just not going to look very fun. But play with me, okay? Because once you see how it works, then it's not hard anymore. Okay, so any digit that isn't a 0 is a significant figure. So you always count non-zero digits. Here, see? 1, 3, 3, 1, those are not 0, right? 4, 2, 1, not 0. You count those. And then there's the zeros. 3 kinds of zeros. Interior zeros, like this guy. It's between non-zero numbers, non-zero digits. So those are always significant. You always count those. This one's trapped, it's interior, it's on the inside, those, okay? And then we have leading zeros. These are the zeros that come at the beginning of the number. So the numbers that come, the zeros that come at the beginning are never counted. They're never significant figures. They are placeholders. Because if we didn't have the zeros there, if I wrote 0.23, well, how many spaces did I leave there? What am I doing? Is that just a weird way of writing 0.23 or what? We need the zeros to hold the decimal place. Yep.
That's why when we write it, we do 0.23, but then we put the negative and the positive numbers.
Yes. So scientific notation.
Yeah.
Right? So that's why scientific notation is really great, because it gets rid of all the zeros that we don't need to look at. So we could put this number in scientific notation. There's a dynamic study module in Mastering Chemistry that will help you review that. I'm not specifically going to lecture on scientific notation. But the basic idea here is we're going to take our number and we're going to put the decimal place after the first digit that isn't a 0. So, you always read left to right. We come to a 2. Okay, 2, and I'm going to put the decimal point there, and I'm going to write down the rest of the digits. So 2.3 times 10 to the something. And what we're going to do is we're going to look at, I had the decimal point here, here, and I moved it 1, 2, 3, 4 places. I moved it over 4 places, so the exponent is going to be 4. Most people don't have problems with that. The problem then is it positive or negative?
Negative.
It's negative. How do you remember? Well, this is how I remember. Is 0.00023 a small number or a big number? It's a small number. How do I feel about small paychecks?
We don't want
Negative. I feel negative. So this being a small number needs a negative number, exponent. Okay. So here, we don't have to show those anymore because this exponent is doing all the place holding for us. So in scientific notation, all the non-significant zeros disappear. It's really kind of nice. So leading zeros, never count those. Trailing zeros. So the way I describe this is a little different than what the book says. The outcome is the same. This just makes more sense to me. If you like the book way, fine, do it that way. So these are the zeros at the end. So when we have zeros at the end, you want to see, is there a decimal point actually written in the number? So this number has a decimal point. This one does. These numbers don't have a decimal point written. Now, we know where to put the decimal point, but they didn't actually write the decimal point. So if they wrote a decimal point, then those trailing zeros are counted. If there's no decimal point, the most correct thing to say is those are ambiguous. We're not sure. So 300, the person might have measured that to the nearest 100, or they might have measured it to the nearest 1, whatever, but we can't tell. And so what we're going to do is we're going to assume the worst and say, well, we can't tell, so those are going to be not significant. And so in this number, we wouldn't count the zeros, we'd only count the 3. Yeah?
So don't they use a bar, like I've seen that?
Yes. So what we do sometimes is we'll underline the uncertain digit, which is the last significant figure. And so, you could write 3 and underline that 0, which is communicating that the 0, that first 0, is the uncertain digit. The problem with that is that's not a universal thing, right? So the better way to do that, if you wanted to indicate that the first 0 was significant and the second one wasn't, is to use scientific notation. We've got 3.0 times 10 to the 2. So let's move it 2 places. So that, look at this follows the rule now. There's a written decimal point. If you're going to have trailing zeros in scientific notation, there will always be a decimal point. So these guys count. This is where all your non-significant zeros are hiding. So this is going to take some practice. We also need to talk about exact numbers. There's different kinds of exact numbers. Counting integer numbers that are part of an equation and defined quantities. Okay. How many pieces of paper? 3. Are you sure?
Yes.
It's not 2.5. There's 3 pieces, right? You could count pencils, or how many fingers? 2 fingers, right? Those are discrete objects that we can physically count. 1, 2, 3, 4, 5. So there's no uncertainty in that. It's an exact number. Well, what if we need to know how many significant figures it has? Well, you could say it has an unlimited or an infinite number of significant figures. The other type is when you have an equation like the density, that's chemistry. The diameter of a circle is equal to 2 times the radius. That is an integer as part of an equation. That's an exact number. Or defined quantities. 1 gallon is exactly equal to 4 quarts because it was defined that way. Now with our unit conversions, if it's within the English system, quarts, gallons, feet, inches, those sorts of things, then it's probably exact. If it's within the metric system, it's probably exact. Most of the ones going in between are not. There's a couple exceptions. So let's practice this here. How many significant figures in each number? 554 kilometers. 3. What's tempting there is to say that's exact because it's a whole number. But are kilometers objects that can be counted?
Yeah.
Not objects. It's a measurement. You can count, how many kilometers, but it's a measurement, and so it's not precise. I mean, it's not exact. Okay, how about 7 pennies? That's an exact number. So I could say this is exact. But, what if you're doing an online homework problem and it wants a number? It says how many. Exact is not an answer to that. How many? Infinity. Infinite, unlimited, right? So there's a question on the homework, on the worksheet where it does this. And so those exact numbers, I'll take exact or infinite. How about this one? 1.01 times 10 to the 5th meters. 3. The times 10 to the something part of scientific notation is placeholding. So we're not going to count that, but you count everything before the x. How about 0.00099 seconds? 2. Leading zeros don't count. 1.4500 kilometers. 5. There's a decimal point. Do I need these zeros to hold the decimal point? No, because it's written there. Why did I write those? Because it's measured. I'm certain about this 0, and this is where my estimate is. That's why I wrote them there. Okay. I didn't need them to hold a place. How about 21,000 meters? 2. We're going to say 2 because we can't be sure about those, right? This is a poor way of writing a number. But we definitely need those zeros to hold the decimal place. Otherwise, if we didn't have those zeros, 21 and 21,000 are a little bit different, right? We could get rid of those by putting that in scientific notation, 2.1 times 10 to the, and the decimal point would originally have been there. 1, 2, 3, 4. So this is a 4. And is it positive or negative? It's positive because 21,000 is a big number, and I have positive feelings about big paychecks. So we'll get some practice in the worksheet doing this. Okay. Now we're going to do operations. So the result of the calculation should carry the same precision as the original measurements. So there's 2 different rules here. One is for multiplication and division. One is for adding and subtracting. Because if you think about it, multiplying and dividing are kind of like opposites of each other, right? And adding and subtraction are kind of like opposites of each other. So those go together. So when we're talking about multiplying and dividing, we are counting the number of significant figures. So we're looking at the factors that we're multiplying or dividing, and we're going to see which one has the fewest number of significant figures, and that's what the answer is going to have. So here, this one had 1, 2, 3, 4. That's an interior 0. And this one, 1, 2, 3, 4, 5. This one has 2. That leading 0 doesn't count. Why do we write that 0? It's to call attention to the decimal point. And I would encourage you to always write a 0 before your decimal point, because sometimes, the little dot you make with your pencil is really small. And if there's a 0 there, then we're going to go looking for it. So you do this on your calculator, you get all these digits. But we're looking at which one has the fewest sig figs. It's 2, and so then we have to round this to 2 significant figures. And so this result would have uncertainty in the 10th place. Here we're dividing, again, 5 and 3 sig figs, which is smaller. It's the 3, so we take this number and round it to 3 significant figures. For adding and subtracting, instead of counting significant figures, we're counting decimal places. So we're looking at the numbers being added or subtracted. We're going to find the one with the fewest decimal places, and that's how many decimal places we put in our answer. So it can be helpful initially to stack them up like this. And let's go through and underline the uncertain digit in each of these. So which is the uncertain digit in 2.345? The 5. It's the last digit. Oops, that's not very good. And in 0.07, what's the uncertain digit? It's the 7. And in this one, it's the 5 again, right? It's the last one. So if we think about adding this in our head, and I don't want you to add things in your head, because we make mistakes. Right? Just use your calculator. This is not math class. So if we were adding this in our heads, we'd say, well, there's nothing there and 5, so that's 5. Well, this 5 was iffy. So what's this 5? It's also uncertain. Okay, well, let's underline that to indicate that one's uncertain. Here I'm adding an uncertain 5 to nothing and a 7 that I'm certain about. So that gives me 12, but am I sure about the 2? No, because I wasn't sure about the 5. So this can't be 12 with certainty. Next column. I'm certain of the 4, not certain about the 7, certain of the 9. So when I add these up, am I certain about the 1? No, because I had one uncertain digit in there, so this is also uncertain. Now the next column, the next column, 3, 0, 9, the 9 and the 3 are certain, And this is not considered a significant figure, but is there any question about whether that's 0? No. So 3 plus 9 is 14. I'm sure about that. I'm certain about that. So everything to the left of this, those are all going to be certain. What we want to report is all the certain digits and one uncertain digit. So we stack them up here, and then we drew a line where at the shortest one. Now, this one only had 2 decimal places. And so then that's where my number is going to end when I round it. So I'm going to call this 5.41 because there's uncertainty in the hundredths place. And doing the same thing over here with subtracting. Usually you'd see this written out like this. And you're subtracting, so you're looking at decimal places. And you say, okay, this number has 1 decimal place. This number has 3 decimal places. So that means my answer should have 1 decimal place. So you do it on the calculator and you write down what your calculator says. And then you say, but I'm only supposed to have 1 decimal place, so I'm going to underline that because that's where it should stop. And now I'm going to round my number. I'm looking at the next digit. Is it 5 or greater? Yeah. So I'm going to round up. So this is 5.7. Okay? Rules for rounding. If the first digit you're getting rid of is 4 or less, or you could say less than 5, you just drop it. You're rounding down. If it's 5 or greater, you're going to round up. This is very important. When we round a number, we don't want to change the overall magnitude of the number. So if we need to round $24,938.99 to 3 significant figures, what happens sometimes is students will tell me, well, I'm supposed to keep three significant figures, so 249. So somebody is selling a car, and we're just going to go with 3 sig figs, and I'm going to offer them $249 for their $24,000 car. No, it's ridiculous, right? But somehow when you're doing it with grams of something, you're like, this is okay. No, it's not okay. So what's the problem here? 3 significant figures. I'm rounding to this place. If I'm rounding over here past the decimal point, I'm fine. If I'm rounding in the ones place, I'm okay. But if tens, hundreds, thousands, any of these other ones, I could make a big mistake like this. So in order to round this and keep the same magnitude, I would have to replace those digits I got rid of with zeros. 24,000, oops. Not many, maybe not that many zeros. 24,900, right? Rounding this number to the nearest 100, you get 24,900, not 249. So the best thing to do, anytime you're rounding past the ones place, put it into scientific notation and round it at the same time. So putting this number into scientific notation, I write the 2. The decimal point always goes after the first non-zero digit. So it's never going to be 24.9 in scientific notation. 2.49. Keeping 3 digits, 2.49. Those are my 3 digits. The 3 is the one I'm dropping, and that's going to round down, times 10 to the, and I move the decimal place. So the decimal point was here. It wasn't over here. We're not going from the end of the number. We're going from the decimal point, which is sometimes the end of the number, but sometimes not. So I'm moving it 1, 2, 3, 4 places. Times 10 to the 4. Positive or negative exponent? Positive. That'd be a great monthly paycheck. Wouldn't that be awesome? 2.49 times 10 to the 4. Okay.
So your answer would be both of these? Or it depends on what it asks you to do?
Good question. So would your answer be both of these or either or? This is acceptable, but it's not ideal because it's a little confusing. Those zeros technically are ambiguous. There are times when you'll have like one significant zero and some insignificant zeros, and there your only option is scientific notation. But sometimes you could go either way, but 249 is definitely not right. So just practicing the rounding a little bit. We're only looking at the first digit that we're getting rid of. So rounded to significant figures. That means I'm keeping the first two. So I look at the next one that I'm dropping. 7 is 5 or greater, so I round up to 4. Here, again, keeping the 3. The next one is 4, so that one's going to round down. 5.35, here this is 5 or greater, it's going to round up to 5.4. What if I have a whole bunch of digits here? I'm keeping the 3, just look at the first one. Just the first one. Ignore all the rest of them. Just the first one. It's a 4, it rounds down. Sometimes we do multiple step calculations. Thankfully, we don't do this a lot in lab, but there are some, and so we do need to become familiar with this, and there's several things on the worksheet about doing this, so we need to learn this. We're not going to round each intermediate step, because if we round with every calculation, by the time we get to the final answer, we could have more uncertainty in that number than we should because of all this rounding that we did. So what we want to do is we want to carry all the digits with us until the very end and then round the number. So what you do is you do that calculation, you write down what your calculator says, and then you go think about the sig figs. So here I've got multiplying, and then here's subtracting. So the subtracting rule says fewest decimal places. This one has 3 decimal places, this one has 2. So the result of that, 0.479, should only have 2 decimal places. I'm going to underline that to remind myself that's the last sig fig, but I'm going to keep the 9 to avoid rounding errors. Now I've got all multiplication. I've got 3 sig figs, 4 sig figs, 2 sig figs. So I get my answer, and then I round it to 2 significant figures, and I come up with 19. So there's some examples there. I'm not going to do those. We're going to wrap this up here. Accuracy and precision is related to measurements. So accuracy says how close your answer is to the correct answer. Precision says, I made a bunch of measurements. How close are they to each other? You can have accuracy and precision. You can have one or the other, or you can have neither. We'd like to have accuracy and precision. So here's looking at some data. 3 students weighed a block of lead. We know that its true mass is 10.00 grams. This is what they came up with. Well, looking at it like that, it's a little bit hard to see what's going on. This is why scientists often use graphs to make things that make these numbers a little more visual. So if we use bar graphs, here we have the mass that's measured by the trial number. And so this first student, 10.49, 9.79, 9.92, 10.31, those results are all over the place. Right? They're not very close to each other. So this is not precise. They're scattered all over the place. So sometimes we think of this as being, like a bullseye. We're shooting arrows, right? So where are these arrows hitting? They're hitting all over the place, right? You don't want to be anywhere near this person. So how do we assess accuracy? We're going to look at the average of all of these. This person got an average of 10.13. Well, the true value is 10.00. Where's the uncertainty in that 10.00? It's the last zero. So if our number is accurate, it should only have uncertainty in that last digit, the second decimal place. This differs in the first, that's not what I meant to do. This differs in the first decimal place. So this is not close to being correct. So this is inaccurate and imprecise. This student got these results. And see, they're all very close to each other, right? So that one is precise. But then we look at the average, 9.79. Okay, that does not differ in the second decimal place. So this guy was over here, sitting right on top of each other, but just like way off the mark, right? Very precise, very consistent, but something's going wrong here. And then this last student, all the values are close to each other, and the average is close. So here, 10.01, well, the 1 is uncertain. And in our true value, the 0 is uncertain. So these numbers are essentially the same. So this student is hitting bullseyes. Precise and accurate. There are sources of error in all of our measurements. One of them is random error. Random error has an equal probability of making your number too big or too small. So if you make a whole bunch of measurements, about half of them are going to be too big and half of them are going to be too small. So if you take the average, the random error goes away. And that's one of the reasons why we often measure things or run different trials. Multiple trials will do 3 or 4 and average them, because that helps to get rid of some of that random error. Then there's also systematic error. And this is like student B. All these values are close to each other, but they're all too small. This student is doing something wrong, or the balance isn't calibrated. Something's going on here. All the values are too small. So systematic error is something that, if you find that, then we have to figure out, well, what's going on and how can we get rid of that.